Hello everyone. In this video we will be talking about continuous random variables and how that links to probability distribution. And first we'll be talking about the difference between discrete and continuous random variables. Okay, some examples of discrete random variables could be the number of fours that are rolled, the number of males or females on a committee. So in previous videos we discussed the discrete random variable for probability distribution, the number of fours rolled, the number of males or females on a committee, the outcome of a six-sided die being rolled. So the outcome of a roll from a six-sided die. So for example, you could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6. And if we did a quick histogram, each of those has a probability of 1/6. So the outcome of a 1 being rolled has a probability of 1/6. And all the way to the outcome of a 6 being rolled. So there's a quick probability histogram for the outcomes of a roll from a six-sided die, and whether you roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6, you have a probability of 1/6 for that occurring. And the sum of all these probabilities, if you notice, is 6 out of 6, which is 100%, which shows that the distribution is complete. So this is an example of a uniform probability distribution, and the sum of the probabilities is 1. And the outcomes are discrete. A 1, a 2, a 3, a 4, a 5, or a 6. These are discrete outcomes. So this reminds you of discrete random variables that we previously studied in previous videos. This video is focusing on continuous random variables. Okay, now let's consider a continuous random variable. For example, time, and let's use a data set that consists of the time it takes students to complete a test. So let's say the data set consists of 65 minutes all the way up to 95 minutes for a particular class to complete the test. So the continuous data can be grouped into intervals, and let's say that this is what the histogram would look like. So we would have 0 minutes here. We'll have a break in our scale. The lowest time to complete was 65 minutes. The greatest time to complete was 95 minutes. And let's say that it's a uniform distribution where all outcomes were equally likely. In other words, each student completed the test at a different time. So therefore, we would have a visual of a horizontal line. And the probability for any given continuous random variable is not calculated. However, it's not determined just yet. However, since the entire data set consists of between 65 and 95 minutes, and recall the previous concept that the sum of the area or the sum of the probabilities in this distribution will equal 1, will allow us to determine what this uniform probability is. In this case, for a continuous random variable of test time. So this is the time it takes to complete the test in minutes. And if we consider this like the area of a rectangle, so the area of a rectangle would be length times width. In this case, the length is the base of this rectangle, and the width is the height of this rectangle. And in this context, the base would be 95 minus 65. The height is the uniform probability that we're trying to determine. And the area of this rectangle, the sum of the probabilities, is going to equal 1. So we could rearrange the algebra. 1 will equal 30p. And you divide by 30. So 1 over 30 will equal this uniform probability. And as a result, we just found the probability for a continuous random variable in this data set that consists of test time. The time that it takes students to complete a test in this data set is between 65 and 95 minutes. And if we zoom out, we can see the big picture there, that this uniform probability is 1 over 30. And that concludes the first part of this example. Let's call this part A. Okay, next in part B, we're going to calculate what is the continuous random variable probability that a student in this class takes less than 72 minutes to write this test. Okay, so we consider that the uniform probability is 1 over 30, and we now, if we draw a little sketch on the side here, 65 to 95, the uniform distribution, the probability, that's the uniform probability for any given test time is 1 out of 30, and let's arbitrarily say that that's where 72 is, and if we close off our rectangle, it's this area that we're looking for. So the probability that the test time will be less than 72 minutes equals the base of 72 minus 65 multiplied by the uniform probability of 1 over 30. So that becomes 7 times 1 out of 30, which becomes 7 out of 30. So the probability that a student in this class takes less than 72 minutes to write this test is 7 out of 30 for this continuous random variable. Okay, the next part, what is the probability that a student will take more than 90 minutes? So, probability that a student will take more than 90 minutes is going to equal the area under the curve, in this case under the uniform probability. Again, we're going to take our base times our height. In this case, our base will be the upper limit of 95 minus 90. That's the base, multiplied by the height, which is 1 over 30, the probability, the uniform probability. So that's going to be 5 times 1 over 30, which is 5 out of 30. The probability that a student will take more than 90 minutes is 5 out of 30. Okay, next let's consider how many possible values for the continuous random variable, in this case test time, are there? Is there a specific number of test times that are possible? Is there a finite number that are possible? It's not discrete, so we're going to have to say that it's infinite. There's an infinite number of possible test times. For example, 65 minutes, 65.1 minute, 65.05 minutes, all the way up to our upper limit of 95 minutes. So how many possible values are there for this continuous random variable test time? There's an infinite number. Infinite number. That's what makes it continuous. We could break down the barrier, the space, for example, between 65 and 65.1. Actually, this number is in here, 0.05. We could break it down and continue to break it down further by going very, very minute into the decimal places. So, how many are possible? Infinite number are possible. Next, let's consider if we can find the probability that a student takes exactly 90 minutes to complete the test. Now, in reality, is it possible? Yes, it's possible. However, we are considering this using a continuous model. And according to the continuous model, if the piece of data is exactly 90, and we're using the area under the curve, in this case it's rectangular because it's uniform, and we're using the model of the base times the height becomes the area under the curve. And recall, for the entire data set, which starts at 65 and ends at 95, it's 100% complete, which led us to a uniform probability of 1 out of 30. So under this model, exactly 90 would have a base of 0, and the uniform probability is 1 out of 30, which means the probability that a student takes exactly 90 minutes, well, it's going to equal 0. It's not possible to take an exact value under a continuous model. We're going to have to resort to previous strategies and use a discrete model if we want to find the possibility of exactly 90-minute test time. So that's option 1. So under a continuous model, is it possible? No, it's not possible unless we consider the probability to be 0. Under a discrete model, is it possible? Yes, it is. It's possible under a discrete model. So the question is, can we do this with a continuous model? Well, for exactly 90, no, we cannot. We'd have to resort to a discrete model. But if we create an interval, then we could use a continuous model. And this is called continuity correction, where you decrease the exact number by 0.5 and you increase the number by 0.5. And as a result, we have an interval now, a continuous span. It's no longer a discrete value that we're trying to calculate. Exactly 90 is not possible under a continuous model because it's a discrete value. So our first option is to resort to previous strategies for discrete random variables. However, if we want to use a continuous model for exactly 90, then we have to create an interval for 90, which is 89.5 to 90.5, which gives us a base and a height other than 0. So in this case, the base would be 90.5 minus 89.5. And our height is our uniform probability. So this becomes 1 times that uniform probability, which is 1 out of 30. So the probability that a student will take between 89.5 minutes and 90.5 minutes is 1 out of 30, and this includes exactly 90. Is this the probability for exactly 90? No, but it's the probability of the time span of a minute, which includes 30 seconds before and 30 seconds after 90 minutes. So is it exactly 90? No, we'd have to use a discrete model. However, by creating this interval, we could come up with a second method. Instead of a discrete model, we could use a continuous model to find the probability for approximately 90 minutes, between 89.5 and 90.5 minutes. That concludes this video on continuous random variables. We outlined the difference between discrete and continuous. Then we linked it to probability for a uniform distribution. In our next video, we will talk about continuous random variables and probability when the distribution is not uniform. It might be normal, it might be skewed left or skewed right distributions. Nonetheless, we will address continuous random variables and probabilities for different types of distributions. That concludes this video on uniform distributions with continuous random variables. Thank you for watching. I hope it helped. Please leave your comments in the box below. If you enjoyed this video and you'd like to see more of them and you'd like to be updated when they're posted, please subscribe to the channel and have a great day. You guys are awesome.